So we'll do some Hbonds. So we're going to use an MD analysis submodule. So if I do from MD analysis.analysis, I say that word a lot. Import Hbonds. This submodule has a hydrogen bond analysis class. Typically, the MD analysis submodules have this kind of form. They come as a class that you then usually need to read the documentation for to get a sense for how they work. I think for a while we did try, and I think we converted a lot of these things over to a pretty standard form, but some of them kind of fall outside the realm of that standard form, so they sometimes are a little strange. But this one in particular takes as input a universe, a selection 1 and a selection 2, and basically what it will do is say, it will give me for the entire trajectory, the hydrogen bonds between this selection, so say this is one domain of the protein, and this selection, which is the other domain. So it'll gather up all of the hydrogen bonds present in those, for each frame, between those domains. So not within them, but between them. So what I need to do to use this is I need to define a couple things. And I'm going to go ahead and write it out as a function, because normally we would kind of prototype this, and then once we get something that works, we would then stick it in a function and then apply it to all of the simulations. But in this case, I kind of know exactly what I want. So I'm going to say get Hbonds. This is going to take as input a sim, so a single simulation. And we're going to do the same try except statement that we did before in building our universe, because we know some of these will fail. But we're a little lazy to sort them out ourselves, or at least I am. And I'm going to steal that code block that I used before. It's the same idea. Oops. Then, what we want to do is we need to define a couple domains. So I'm going to say domain 1 is equal to this selection string. And because this is a specific protein, it's a bit of a hard-coded thing. I know it's going to be res ID 29 to 100, 190 to 295, and 360 to 466. And domain 2 is going to be the remaining atoms of the protein that have a secondary structure. These are going to be res ID 100 to 190, 295 to 360. And the business end of this function is going to be to use the hydrogen bond analysis class that we just imported. And what we need to feed it is our universe, as we saw in the docs. The first selection we want to use for the first domain, and the second selection we want to use for the second one. And because I know this takes a little while, I'm going to say it takes another argument, which is step, just to say how many frames, or rather, what is the step between the frames you want to analyze should be. I'm saying, get me hydrogen bonds for every 10 frames. I don't want to get it for every single frame, because it will actually take quite a little bit of time.
You can also make it faster by say something like updating is false. So
that is if things don't move much, though, right?
Well, it will not recalculate the groups because you have fixed groups, but the default is updating true because people often use water within a certain distance.
Gotcha. So let's do update selection false and update selection to false. So what Oliver is referring to is that these particular selections I've chosen happen to be static. Like they're not going to change with time. Res ID 29, it's still going to be res ID 29, no matter what timestamp I'm on. But you can do selections in MD analysis that are give me all atoms within a distance of this other atom. And that, of course, will change in terms of what result it gives depending on the frame. And so that would be the case of like if you wanted H-bonds between a protein and the surrounding water. Because you say, get me all the waters within some shell, within some distance of the atoms of my protein. And that will be very dynamic. So what we're saying is here, don't reapply the selection, just use the resulting atom group from it so you don't have to reparse the string every time. So it should run a little faster, basically. We can get away with it. And then I just, at the end, I'm going to call hb.run, hb.generate table. For this analysis, it has this method that it needs to generate a table. And I would understand that from reading the doc, which I did a long time ago. And then I'm going to make a data frame out of this table. So that's my function. I can then apply this, let's say I apply this to a single sim just to see how it works. So if I take B0 here, and call get Hbonds on it, see what it looks like for this to run. Oh, that is pretty fast. Okay. That's a lot faster than when I did this last night. So we might be able to get away with doing every step. Just kind of curious. Yeah, that's not bad at all. So that's for a single simulation, though. We have like 30 of them. So the way we're going to execute that is to call map.
If you pass, I think, verbose is false, then you won't have lots of these status reports coming up.
Okay, I could do that. So this is the result of the Hbonds analysis. So each row corresponds to a hydrogen bond in a particular frame between two particular atoms. Where here's the donor index, these are the atom indices, there's the acceptor, there's the res name of the donor, res name of the acceptor, and there's the corresponding atom that was playing that role. There's the distance, and then there's the angle. So this data frame that results from this is pretty information rich. We can do a lot with it. What I'm going to do is just do one particular thing with it, but I first need to obtain it for all of my simulations.
What's SD?
SD?
Yeah, it was one of the acceptor atom.
South Dakota?
Sulfur, it's a methionine.
It's late in the day. So let's go ahead and run this. We're going to use 10 processes. I believe Casey will be giving a presentation on Dask next week. So that would be an alternative way in which I would execute this if you wanted more cores. Use multiple machines to compute the same work. So we'll let that crunch. Yamsolo is working hard. And in the meantime, I'll finish the stuff that we need to put in the form we want, which is kind of gnarly. So with pandas, sometimes the form it's in is not the form you really ideally want it in. So the resulting data frame we get back is pretty information rich, but I only want certain things out of it. In fact, what I'm interested in is what is the number of hydrogen bonds.
You got it here.
Oh, it's fine. Okay. So what I want is the number of hydrogen bonds for a particular frame. So if we notice from this data frame here, this example, for each row, or rather for each time, there are actually multiple entries, because for each time there's multiple hydrogen bonds present between those domains. And so what I want to do is basically get a count of the number of hydrogen bonds present for each unique time value. So how many are there for 0.5? How many are there for 1.0? How many are there for each one of those? And then I could actually do some kind of figure from that. So I think we got what we wanted here because I put that catch, that try catch in there. Yeah. So we got a list of data frames now. We can use these in the same way we did before to build out a big data frame. So if I do pd.cat, name, Hbond for sim, Hbond, and zip. So that gives me now a giant data frame that has all of that data put together. So we've got this index out here, we've got time here. We could just use this as one unit instead of having to deal with multiple data structures. So this can then be pulled apart in pieces. I did some really gnarly stuff with this to get it in the form I wanted, so bear with me on this. So what I wanted to do was I want to reset the index. So that I drop that useless index that was in the middle of there. So by default, pandas will put an index that's just 0, 1, 2, 3, 4, 5. I just dropped that one out of the thing, so now it's gone. Now I want to reset both indices. So if I do this, that will turn sim names and time into columns as opposed to indexes. And I'm going to set it's completely unnecessary. Oh crap, no, that's why I did it. Alright. So I set them both, I reset the index to get all columns, and then I set the index to be specifically sim name and time, instead of time being a column. Sim names. There we go. So this gets my data frame into a form that I want it to be. When you're using pandas, often, at least I find I often do this, where I reset the index, make everything a column, and then set a new index based on what I'm trying to go for. So sometimes you might find yourself choosing a different index in order to perform one particular task and having a completely different index for a different one. And you can kind of just shift the data structure around and get it into a form you need to get. So I'm going to take this guy, and I'm going to call it counts, because what I want to do actually we're going to call this Hbond, and I'm going to select out the distance column just because I need at least one column here, and I'm going to say let's group by the index. So let's group by these values in our index, and then let's take a count, and we'll see what the result looks like. So what we get is we get a number here, which corresponds to the number of Hbonds in, for example, simulation 001 at time 0.5. So that was how many Hbonds there were between those domains. And so this series object gives you the number of Hbonds for every frame, for every simulation, going all the way down. So we can use that to create something interesting. So what I'm going to do with that is I'm going to say counts.index. We're going to we're going to call this resultant series count, see how it's up.
Why are you using distance?
Just because I had to choose something. I could have chosen any column in there, and it would have worked just fine.
Oh.
Because we're actually interested more in how many are there for a particular index entry,
Oh, I
not
see.
so much the value. Be fortunate. I'm going to reset the index to something else. You can create a multi-index from tuples, since this one has a really ugly index now. We're kind of doing pandas surgery at this point to fix this into a form that we can really use. So that's a much better looking series. It has this index back and the counts there. And I'm going to go further and I'm going to say, let's drop a level.
What's dropping the level do?
We'll see here. So if we now look at counts, now we just have now we have an index that repeats itself, which is perfectly fine. So basically we drop that outermost level, and what I want to do with it is I'm going to use a Hbonds joint plot. So Hbonds is a library that wraps around matplotlib and gives you a lot of nice statistical plots that are already pre-built in a way. So you can, instead of yourself implementing something like I'll give you a sense. So instead of implementing a lot of these different types of statistical plots yourself using matplotlib from scratch, you could use Hbonds built-in stuff to produce, for example, this is a two-dimensional histogram essentially. And you can make it using a joint plot, which is what we're going to do here. Hbonds offers a lot of statistical visualizations that are easy to build given your data. So if you're using pandas, it actually becomes quite easy to make use of these to produce a nice figure. Things like this. So we'll go back to our notebook. I'll import pandas real quick and we'll make an export. Not pandas, Hbonds. And now if I feed joint plot my counts, we're going to use the index as our x values for this, counts itself as the values, and kind equals hexbin. This will give us something that looks kind of like this. And the way to interpret this figure is that on the y-axis we have, this isn't actually distance, let me just rename that. It has to do with the name of counts. Since this series still had the name distance attached to it, we can rename it, because this now is actually a count. I'm going to call it number of Hbonds. So now this will actually give us the right thing on the y-axis. The x-axis is actually time. So if we wanted to fix that too, we could do it. Yep. So we basically rename the index into time. So now our figure should be a little bit more understandable. What this says is, on the y-axis, this is the number of Hbonds present between these two domains. On the x-axis is time for simulation. And what the darkness of the blue represents is how many simulations that number was the case for at that time. So you could say that the coloring gives you a sense of basically how many that showed up for. It's basically, this is the distribution. These slices of the distribution show you where the simulations sit on average in terms of number of Hbonds at a particular time. Yeah.
What does the legend mean?
the legend. So what Hbonds joint plot will do automatically is try to calculate certain summary statistics. So for the joint plot, this would be, it's giving us a Pearson coefficient. I don't know exactly how to interpret it in this context. I probably could just switch it off because I'm actually doing it. But anyway, this figure represents basically what we see in terms of time for Hbonds. So we see that initially we actually have quite a few Hbonds. Looks like they then sort of drop off a little bit as time passes, and then they start to rise again as the simulations proceed.
Can you do a KDE from that? Does this make sense?
You should be able to.
Instead of KDE, instead of Hbin, does it take KDE?
Let's try it. Oh, sorry. Let's do that. Joint plot. Let me see. Is that the if we go to the API docs, that'll tell us what joint plot can take. So it can take kind KDE. Okay. Sorry, I should just listen to you over. So what a KDE will do is it'll do a kernel density estimate instead of doing a hard hex bin. So instead of binning, so a hex bin is basically a histogram, right? So there's discrete bins, and you're either in it or you're not in it. What a KDE does is builds up what are called kernel density estimates. So it basically puts a Gaussian wherever there's a point, and based on the sum of those Gaussians, that's the darkness you'll see here. So it's kind of a smooth operation for a histogram. So this is the same data, but kind of smooth with KDEs. Now, whether or not this is actually useful information or is actually an observable that's robust is another question entirely. The point is we were able to get here by going through the route we took. We made use of a lot of pieces. We treasure around our file system. We used a library for pulling apart trajectory data. We used visualization. We used multiprocessing. But this is kind of the iteration loop for doing science, at least during my PhD it was, where you sort of try something, you get something like this, you ask yourself more questions, and then hopefully we can build from that, keep going. All right, so maybe that's the real end of my talk. It's now 4 o'clock.
Well, thank you very much, David.
Yeah, of course. Thank you. I'll stick around for questions if you guys have them, but yeah, thank you. Have a nice life.
I have a question.
Yeah.
So is it possible to measure the number of Hbonds in first hydration shell as a function of simulation time?
Yes. So what we could do, instead of making our selection domain 1 some domain of our protein and domain 2 some other domain, instead what we could have done is made domain 1 the protein itself and made domain 2 all the waters in the whole system, or rather not the whole system, all the waters probably within the first hydration shell distance, so maybe a few angstroms basically. And that second selection would work just fine for getting you that hydration.
No, my point is that if your both selections you just first hydration shell, so you want to know the hydrogen bond between waters.
The first hydration shell with the first hydration shell, the hydrogen bonds of that group with that group.
Yeah.
I think based on how it's written, it should work. Yeah, because it doesn't really care that these are the same. But it comes down to how the Hbond analysis is written. So fortunately, this is all written in Python, so worst case kind of scenario, we can have a look. You can also just try it and see if the result looks like it's what you'd expect given. I'm thinking it should work with the way that analysis is written, because I don't think it cares whether or not these domains are actually the same. Does that answer your question?